Hello everyone, and welcome back to another Stratagoy video. This time we'll be following up our introductory discussion on the basics of a D6 roll by now turning our attention to common in-game mechanics impacting the uniform distribution we've come to expect of a D6. If you haven't yet checked out that video in need of a refresher, feel free to click the link above, but in the meantime, here's a short recap of what we've already covered. We began by discussing what it even means for a dice roll to be fair in the first place, but then using this assumption for the rest of our breakdown, and those for the rest of this MathHammer series in general, we turned our attention to aspects like the uniform distribution and different ways to visualize it. We then spent the rest of the video dissecting the different measures of central tendency we have in mathematics, those being the mean, median, and mode, and how we might better use them to make sense of probability in our games of Warhammer. Finally, we concluded by applying these same concepts to a 2d3 roll, which we examined in a previous MathHammer video as well, see the link here, and then comparing it to what we saw with our d6 rolls. So now that we're all caught up, here's our friendly reminder that if you want to keep in touch, join our Stratagoy Discord, where Jonas himself and I will be happy to chat with you there. And please do subscribe to the channel and or hit that notification bell if you want to stay up to date. Alright, so in the sections that follow, we'll begin by addressing the mathematical implications of re-rolling ones on a d6, first in terms of its probability mass function, and then with regards to its cumulative impact. This is then logically followed by the usually stronger but also much more mathematically complicated ability to re-roll all failed rolls, not just ones. We'll conclude with some comparisons of everything we've covered up until now and scope out what's yet to come in our final installment of this series. So let's begin by reminding ourselves of what the uniform distribution of a d6 looks like, where each outcome is equally likely at 1/6, as seen in the graph of the probability mass function, or PMF for short. Note that this is simply a visual representation of the chance that you get any one of the 6 outcomes on a d6, not the chance that you get a certain value or higher, which we visualize as a reverse cumulative distribution function, or CDF for short. So let's think through what happens when you're given the chance to re-roll any ones. First off, if you roll any value other than a 1, well, that's too bad, because if you're unhappy with the result, you're stuck with it. So that means there's still at least a 1 out of 6 chance that each value from 2 to 6 is likely to happen on that first roll. But what happens if you roll 1? Well, you get to re-roll it, of course, but that means that you start the whole process over again and now have a new chance, after a second roll, to be permanently stuck with any one of the usual 6 potential outcomes, seeing as we can't repeat re-rolls in Warhammer. So let's compute this probability by first taking the chance that you roll a 1 for your initial roll, or 1/6, and then multiply it by the chance that you roll any one of the 6 outcomes available on a d6. In other words, the chance that you got to re-roll a 1 and it came out as a 1 is 1/6 times 1/6, or 1/36, and this probability also holds for any other value you might have gotten on your re-roll, so for a 2, a 3, a 4, a 5, or of course a 6. Now, how does this impact the probability mass function of our distribution? Well, after realizing that a 1/6 chance is the same as a 6/36 chance, we can see here in this updated chart that by re-rolling ones, we essentially stole 5/36 from the 6/36 that previously belonged to the chance of rolling a 1, and then gave one of each of those 5/36 to each of the remaining values, so for 2 all the way through 6. Making it 7/36 now. Here we have the graph version of this result, where I've color-coded this as orange so that you can better see the impact of re-rolling the ones. Thus, the blue portion of each bar represents the amount of probability for a given value that was generated on the first roll, and the orange is that portion coming only from the re-roll itself. By stacking them on top of one another, we get the full chance that a given number occurs. So, in the end, while the chance of rolling a 1 got cut way down to a 1/6 of its former value, so from 6/36 to a mere 1/36, the chance of rolling each of the other numbers went up a tiny bit, from 636 to 736, or a 16.67% increase for each. One last quick note here is that we can once again calculate the expected value or mean of rerolling ones. As you probably remember, the expected value for a normal D6 roll is a 3.5, so we're expecting this to be at least a little higher here now, but by how much? Now that the distribution, as seen in the PMF here on screen, is no longer uniform, it's a lot harder to compute by simply eyeballing it. So let's do it the old-fashioned way. So we simply take the value of each potential die roll, so 1, 2, 3, 4, 5, or 6, and multiply it by its corresponding chance of happening. So 1 over 36 chance for the 1, or a 7 over 36 chance for everything else, as we already computed. And then we add all those results up. What you end up getting is 3.92, or an 11.9% improvement in expected value over the normal D6. This means that, on average, over a large number of rolls, you're more likely to average a 4 than a 3, whereas before, when it had an expected value of 3.5 for a normal D6, it was 50-50 either way. If this feels a little counterintuitive to you, it's probably because an expected value is often not a whole number, like 1, 2, or 3, but rather some integer value between whole numbers. By contrast, our dice rolls, by definition, can only generate whole number results, which is why I often make sure to emphasize the point that expected values are more accurate for an average over larger numbers of dice rolls, as opposed to any given small number of rolls needed to be made. Without going into talks about variance or swinginess in Warhammer speak, if you're particularly risk-averse, meaning you don't like taking risks, it's good to round an expected value down a bit just to avoid getting your hopes up in crucial moments. Getting back to our PMF for rerolling ones, at first glance this might look like it benefits each of the potential die rolls from 2 to 6 equally, but in real-world outcomes in Warhammer, we're usually looking at cumulative likelihoods, or put in common terms, the chance that you roll a certain value or higher. And in these scenarios, benefiting equally can have different meanings depending on the perspective of whom you ask. As we saw in the last video, this can best be represented graphically by examining the reverse cumulative distribution function, or CDF. And just as before, where we simply went from right to left of the PMF and added the values from a given point up, we can do that now with our adjusted distribution for rerolling ones on a D6, which ends up looking like the graph here. Note that I've split the bars into blue and orange segments, but it's worth pointing out that, seeing as all the results 5 plus or lower represent the combined impact of not only that number, say a result of a 5, but also everything higher than it, so in that case, also the 6, so 5 and 6. So what this means is what we end up seeing is an increasingly large portion for both the blue and orange sections of each bar. I've also summarized the improvements gained from rerolling ones over a regular D6 roll in the accompanying graph here, where, for example, the chance of rolling a 4 plus went up from 50% to 58%. I'll linger a bit longer on this slide so you can take a deeper look for yourself. Moving on, I've listed in the chart here 2 additional ways of looking at the improvement, one multiplicative and the other additive, or in other words, one showing how much of a fractional gain a given roll improved by, so percentage-wise, and the other showing how many additional percentage points were added. For a simple example not seen in the chart, going from 20% to 30% represents a multiplicative improvement of 50%, i.e., the difference between the two, 10%, was 50% of the original value of 20%, so it represents a 50% improvement. So this is the multiplicative improvement. But the simple additive improvement in terms of percentage points, so simply 30% minus 20%, is just 10%. While it might not seem like a big distinction here, especially considering the two metrics are related, it is often very important in statistical talk to clarify which you mean. So going back to the rerolling ones calculations in the chart above to better help illustrate my point and get back on topic, if you simply look at the multiplicative improvement, you'll notice that all 5 desired outcomes, or those from 2 to 6, leaving out 1 since they almost always represent failed rolls, improved equally by 16.67%, as mentioned before. So from this standpoint, none of them ends up benefiting more from the buff than the others. But from the additive perspective, we see a sort of snowball effect as the needed outcome gets lower. So, for example, as we go from a 6 plus to needing a 5 plus and all the way down to a 2 plus, which of course is improving the chance that it'll happen. In this scenario, we see that a 6 plus only improves by roughly 3 percentage points, or from 17% to roughly 19%. But a 2 plus improves by a whopping 14 percentage points, or from 83% to a 97%. This difference between a multiplicative improvement and a simple additive one can otherwise be described as having a scaled up impact. Thus, rerolling ones ultimately has what might feel like a much stronger impact on easier to achieve rolls, like a 2 plus, than it does on harder ones, like a 6 plus, even though they technically all got better by 16.67%, or 1/6. So while rerolling ones does help make your rolls more consistent, it's probably going to be felt much more strongly for 3 pluses and 2 pluses and not so much for your 6 pluses. So this pretty much goes without saying, but clearly rerolling all failed rolls versus only doing so for dice rolls of 1 is a stronger buff. But now that we've got a good sense for how the latter works, let's see if we can work out precisely how much better the former is. The general idea is that we can now choose to reroll all values that fail a given threshold. For example, let's say you need a 4 plus to succeed, in which case you can reroll all 1s, 2s, and 3s, not just 1s. But seeing as this condition is dependent on what kind of dice roll you needed in the first place, so a 4 plus in that scenario, we're going to have to run separate calculations for all possible conditions. So one for a 2 plus, a 3 plus, a 4 plus, and so on. Before we do so though, let's make sure we're on the same page with this general concept. Let's start by comparing rerolling all failed rolls in 2 conditions. Firstly, where a 2 plus is needed, and secondly, where a 6 plus is needed. While a 2 plus is in fact a stronger position to be in for your dice rolls, it actually ends up benefiting way less from a rerolling fails buff than a 6 plus does. In fact, adding rerolling fails to a 2 plus is literally the same as giving it simply reroll 1s, as the only value for which you actually get a reroll on a 2 plus is a 1 anyway. By contrast, whereas rerolling 1s for a 6 plus only gives you a second chance to get a 6 if you roll a 1 the first time, so 1/6 of the time on your initial roll, rerolling fails gives you a second chance 5/6 of the time on that roll. So for a 1 through 5, which functionally represents a much more improved outcome from one buff to the next. What this ultimately amounts to is that for different starting conditions, you have different chances that you'll even have to enter the second stage of dice rolling in the first place, functionally meaning that we have different probabilities associated with rerolling fails for not only 2 plus and 6 plus, but of course everything in between. So let's start with the obvious choice, that of rerolling fails when you just need a 2 or higher. As we just mentioned, this is identical to the situation where you need a 2 plus with rerolling 1s, as the only failed values you can obtain are 1s anyway. Just for thoroughness' sake, I've gone ahead and including those same graphs here one more time, but with the titles changed for clarity. Naturally, the expected value for this scenario is also equivalent to that of rerolling 1s and is thus 3.92. Now, let's get into the more interesting content, starting with rerolling fails for a 3 plus. To start, we'll try a different approach to get to the answer we're looking for, but after that we'll approach the problem the same manner as before. So let's imagine the first roll. If we roll a 3 or higher, so 4/6 of the time, we get the roll we were looking for and don't need to consider the reroll. But on a 1 or 2, so 2/6 of the time, or of course 1/3 when simplified, we do need that reroll. So right off the bat, we know we're going to be successful better than a normal 3 plus roll. But do you have a sense for how much better this will be? Well, on that second roll, we once again have a 4 out of 6 chance of a success. So we simply multiply that by the 2/6 chance that we had to do the reroll in the first place, or that we failed the first time, giving us an extra 8/36 chance that we're successful. In other words, getting a 3 plus, not specifically getting a 3 itself. So let's take a look at the probability mass function for a 3 plus with rerolling fails. Like we saw with the rerolling 1 scenario, the height of each of the failing bars, so getting exactly a 1 or a 2 on the first roll, or the portion that would have been blue, has been equally distributed amongst the successful bars, so a 3, 4, 5, or 6, leaving us with two values, two tiers, 1s and 2s each, now having a 5.56% or 2/36 chance of occurring, versus the other tier comprised of the results for 3s, 4s, 5s, and 6s, each having a 22.22% chance, or 8/36 if you want the fraction. In the graphs here, I've gone ahead and shown the difference between a successful roll on the first attempt seen in blue versus the extra likelihood due to the reroll, once again in orange. If you prefer to see how this works out in chart format, I've included that here as well. In the first row, you have the chance of keeping a given value that happened on the first roll, given that you're looking for a 3 plus. Intuitively then, it makes total sense that neither the 1 or 2 would have any chance of being kept, as you're about to re-roll them in the hopes of rolling higher. So in this chart, I've written it out as 6/36 that you would roll it, but then it is converted to a 0 out of 36 because you are going to re-roll it. So that first roll doesn't have any weight behind it. In the second row, we see the chance of getting each of the 6 values, which has now been reduced to around 6% instead of the expected 16.67%, as this only happens if you rolled a 1 or 2 on the first roll. So with fractions, this would be the 2/6 chance of rolling a 1 or 2 the first time, multiplied by the 1/6 chance of rolling any of the values in the reroll itself, or fractionally 2/36. The calculation for this result is included at the bottom of the screen. You'll notice in the charts to come that for all of these calculations, this second row is always the same value for all 6 outcomes. So once you figure out what it should be, it's pretty straightforward. And lastly, the third row shows the sum of the 2 rows' probabilities, with the fourth row showing this in percentages, giving us our desired answers. Having analyzed the probability mass function, we can also calculate the expected value once again. As always, we simply multiply each possible value by its chance of happening, which you can see here on the screen if you're curious. In short, our new expected value for rerolling fails while looking for a 3 plus is a 4.17, representing a 19.05% improvement over a regular D6 roll, and even a 6.38% improvement over rerolling for a 2 plus, which of course is true for either rerolling 1s or fails, which again are the same. It's important to point out here that this improved expected value doesn't mean that you're more likely to have a successful roll than with a 2 plus, as the 2 plus rerolling threshold is still more likely to go off than the 3 plus rerolling fails. But it does mean that the average die roll you'll end up with after any necessary rerolls will be higher. It's a bit of a niche-y concept to wrap one's head around, but I'll keep including it for thoroughness' sake. Rounding things out for the 3 plus scenario, I'll go ahead and pop the CDF on the screen along with an overall summary of the more important bits we just covered. That said, I advise you to only really focus on the 3 plus column itself, as in this scenario this is mostly all that we care about. Furthermore, while we could make a detailed comparison between each result and those of both the rerolling 1s version and the regular D6 probabilities, I think it's probably better to show those conclusions in a combined graph or chart at the end of our discussion. So now instead, let's just move on to rerolling fails for a 4 plus. The idea is exactly the same as the 3 plus, except of course that now it's triggered on a 3 as well as a 1 or 2, thus creating a new probability mass function, PMF, as seen here, where we once again split the individual probabilities into 2 probability levels. First, the failures each have an 8.33% or 3 out of 36 chance, and the second, the successes each have a 25% or 9 out of 36 chance. Seeing as this is basically just an alternate version of what we've already seen, Perhaps a more interesting comparison here would be looking at the CDFs for both the rerolling fails 3 plus version that we just saw versus the current 4 plus version. But first, here's the chart version of what we've just discussed. Once again, the first row is the chance a given dice roll is kept, the second row is the chance that we get a certain value after being forced to reroll, and the third and fourth rows represent the sums of those values and their related percentages. Again, we see that there is a two-tiered stratification between these chances, one for those representing the values we would need to reroll at 8.33%, and the other for those values we were looking for at 25%. But back to the side-by-side comparison of the CDFs for rerolling fails of a 3 plus and of a 4 plus. What you can easily see here is that while a 3 plus version's lower values, so for a 1 plus, for 1s, 2s, and 3s plus, those outperform the 4 plus rerolling fails for a 4 plus's version, which is in the chart to the right. So if you're comparing the chart to the left for the 1 plus, 2 plus, 3 plus columns versus the chart on the right's same columns, you'll see that it actually outperforms while on a 3 plus. But when you flip it, so looking at the 4 plus, 5 plus, and 6 plus columns, comparing them between the two graphs, you're going to see that the right-hand graph, that for the 4 plus rerolling fails, is actually stronger. Well, why is this? Well, in the 3 plus version, all we cared about was getting 3 or higher, which meant that we stopped trying to get higher values so long as that success condition was met. By contrast, when we need a 4 plus, we implicitly need to reach higher values, now no longer including 3s, which are failures. And thus, in a sense, we were fishing for those higher values, increasing the chances that those higher values occurred, and of course decreasing the chance of the previously acceptable result of a 3 occurring. Well, you might be finding yourself asking, Ryan, this is good and all to know from a theoretical standpoint, I guess, but does this actually have a practical application, or are you just nerding out here? Well, technically that would be a yes to both questions, but there is in fact a practical application. Okay, so imagine you were Gotrek Gurnison, potential allied beatstick to all order armies, and you scored hits on a certain value, but are potentially looking for 6s for extra mortals, as seen in this rule on screen. In addition, Gotrek has the ability to reroll not only fails, but any dice he likes, even successes, which effectively gives him extra opportunities to fish for those 6s, even after successful hits that weren't mortal wound causing 6s scored, thereby risking the chance that your permanent reroll ends up being a failure. While this scenario definitely deserves a deeper dive unto itself, we can simply use the case seen here to illustrate that technically, if you need a given number, say 6s, to achieve a particular effect, if that effect is strong enough, it might be worth risking failure if you're a bit risk-seeking. Or let's say it's the last battle round and you really need to kill that one unit or hero, and it's kind of a all or nothing sort deal. Then maybe you're willing to risk failing, because failing means losing anyway. Before we move on, let's make sure to include the calculations for the expected value given re-rolling fails while looking for a 4 plus, which I'll pop up on screen here. In short, at a 4.25 and a 21.43% increase over a normal D6 roll, this is our highest expected value we're going to achieve out of the re-rolling fails, as it represents the sweet spot between high likelihood, as we've seen in the re-rolling fails for 2s and 3s, and fishing for high values, as we'll see in re-rolling fails for 5s or 6s. Okay, so at this point, by expanding to a 5 plus or a 6 plus, all we're doing is slightly altering the graphs and results we've already seen. So I'm going to quickly just read out those together here. For the 5 plus, you're seeing failed values at 11.11% and successes at 27.78% each. And for 6 plus, you're seeing failed values at 13.89% and successes, or literally just 6s, at 30.56%. As alluded to with the GoTrek discussion we just had, of particular note here is that in the fishing for 6's case, we've increased the likelihood of achieving our needed 6 from 636 or 16.67% to nearly double that at 1136 or 30.56%. Again, balancing this with the risk-reward of giving up your other potentially successful rolls is important, but nearly doubling an outcome in Warhammer is often super rare, so this potential buff shouldn't go ignored. Lastly, on screen, I've listed the expected values of both the rerolling fails for 5's and 6's cases, having left out the calculations from before, which should be easy enough for you to figure out if you just alter a few of the previous details appropriately. And just for simplicity, I presented them in a chart with all of the other results as well, including a regular D6. As you can see, there's a symmetrical pattern here, with rerolling fails for 4's being the high point, as I mentioned before, and each of the rerolling fails values on either side getting equally worse as you get further from that middle point of 4's. This is once again another hint towards the looming topic of variance in our future videos, which is often difficult to get a good feel for, especially with discrete outcomes like dice throws, where we can only get whole numbers like 1, 2, 3, 4, 5, 6 instead of 1.5. In short, though the 2's and 6's outcomes have equal expected values, the 2's are much more consistent, while the 6's are much swingier. To paint this picture a little bit more clearly, let's imagine that what you roll is not only the threshold for what you needed to succeed, but also the damage characteristic for your attack. For the spike-type players out there who balk at the idea of having unpredictable outcomes in their game, they're definitely going to prefer the consistency of 2's even if the output is smaller, with frequently successful damage values of 2 or 3 instead of the big money outcomes like 5's and 6's. But for the risk-seeking Timmies out there who would be much happier seeing their unit go absolute ham on a unit, even if only once in a while, giving up the consistency of 2+s for those juicy high damage jackpots might be worth it to them. This is kind of a simplified iteration of how variance works in the game, but we'll come back to it later in future videos as it's a more complex topic. As we near the end of this thorough breakdown of rerolling fails, we should return to a comment I made earlier about ignoring the individual CDFs for a given success threshold, and instead focus on only the value associated with that given cutoff. For example, as you see on screen, instead of analyzing the whole CDF for a 3+ threshold, we should just extract the 3+ portion of that CDF, as in the circle, and combine it with all our other remaining thresholds similar CDF bars. So the CDF of 2+ for the 2+ cutoff, the CDF of the 4+ for the 4+ cutoff, and so on. So on screen we see the 3+ version. As we see here on the screen now, with the composite CDF in both graph and chart form, which is coming up, I'd like to highlight a few things. First, all the results here are the absolute best they could be from any of the given CDFs for that given value, which makes sense since each was taken from a curve most suited to that result. Second, unlike the individual CDFs we saw before, each blue portion now decreases steadily as we go from left to right, instead of having a shelf effect, effectively representing the original chance you were to roll a given value on a regular D6 roll. So in other words, those blue portions are literally just as big as they would have been on a normal D6 roll. If you have a hard time seeing this, just look at the chart format of the results for the first roll, and you'll see that the numbers are identical to those of a D6, so in the initial roll row there. Third, if we take a look at this chart's row for the value added from the reroll portion, so the second row there, the second line, perhaps the symmetrical nature of the expected values we saw before will come more into focus. As you see here, the portion of the reroll adds not only peaks at a 4+, but also is symmetrical around it. Of course, ignoring the 1+. Though if we included a 7+, it would also be 0%. Finally, and of definitely the most interest to most of you out there, the final results for rerolling fails can be seen in the final row, with a 2+ getting a whopping 97% improvement, or not improvement, but a 97% chance of going off, a 3+ getting 89%, 4+ getting a 75%, 5+ getting a 56%, and a 6+ getting a 31%. Furthermore, as seen in the new chart on screen here, these represent the falling improvements over a regular D6 and over re-rolling 1s. While a 6 plus is getting the biggest improvement of all, at around an 83% boost over a D6. As we discussed before, the difference might not be felt as much unless you're really used to rolling 6 pluses for your units. As such, you'll probably be more impressed with the 33% performance boost of a 3 plus or the 50% boost of a 4 plus, since we're more used to how reliable these rolls are by themselves. And while we're at it, let's go ahead and look at a comparison between all three common options: a regular D6 roll in blue, re-rolling 1s in orange, and re-rolling fails in gray, as seen in this graph. There really isn't too much more to say about this now that we haven't said before, now that we've covered it so thoroughly, but I figured having a nice in-summary graph to wrap things up might be nice for those of you that made it to the end of this video. And on that note, let's call it a day by addressing what's yet to come. In the next and final installment of this series, we'll be addressing the ins and outs of plus minus 1 to a d6 roll, so that would be buffing by +1 or debuffing by -1, and the similar but not quite identical exploding hits. And since this section will go much faster than what we've just covered, we'll use our remaining time in that video to go ahead and compare everything we've covered, including overlapping buffs of what we've seen in this video and that video, and what those distributions look like for your games of Age of Sigmar. In the meantime, as always, don't forget to like, comment, and subscribe, and feel free to join Jonas and me in the Discord for more Warhammer content. Thanks again for keeping up with the math, and until next time, Ryan out.